Meanwhile, the event horizon of a black hole is the point in space where nothing can escape, and it is essential to understanding the nature and influence of black holes in space and time. Both serve as milestones marking the limits of time. We cannot observe any events occurring beyond these horizons. Event horizons and the boundaries of the universe are not the only elements of geodesic incompleteness. If we set aside other complex principles, we find another intriguing similarity between the singularity at the center of a black hole and the singularity right before the Big Bang. Both are singular points with infinite density occupying the entire space. The main difference is that the singularity of the Big Bang exists in the past and encompasses the entire space, while the singularity of a black hole exists in the future with the whole black hole space. If you find this part difficult to understand, let's delve deep into geodesic incompleteness to enhance your knowledge. According to the principle of general relativity, objects not under the influence of forces will follow something known as a geodesic. In Riemannian geometry, a geodesic is the shortest path between 2 points on a curved space with uneven shapes and curvatures, such as a concave or flat curved space. In a sphere, geodesics form a grid that defines the shape of spacetime. They will extend infinitely unless they are forced to terminate at some point. According to this principle, all geodesics will never end except at singular points. This state is referred to as geodesic incompleteness. Geodesic incompleteness refers to the situation when a space has some geodesics or shortest paths between 2 points that cannot extend infinitely but must terminate at a finite point after a finite time. It is often associated with the existence of a region in spacetime where geodesics cannot continue indefinitely but only exist for a finite period or end at a specific point, such as a singularity. This can occur when spacetime has uneven curvatures and is influenced by an extremely strong gravitational force. In the theory of general relativity, singular points are defined as the endpoint of geodesics. All geodesics in the universe come together and terminate at the Big Bang. We call the Big Bang a singularity because it represents the endpoint of spacetime in the past as it occupies the entire past spacetime. A black hole contains a singularity like a spacetime point in the future. It has the opposite direction compared to the model of the universe's formation according to the Big Bang theory. This is the second similarity I want to share with you. All geodesics in the spacetime of a black hole may also terminate at the singularity in the future. It is a process in which matter is completely broken down and compressed at the singularity. Considering that a black hole is an infinite entity, the question of whether or not you will be crushed by a black hole remains unanswered. The singularity of a black hole is the future endpoint that encompasses the entire spacetime under the event horizon, just like how the Big Bang is the past endpoint that encompasses everything outside. When comparing the two shapes, you may notice that they are very similar, with the only difference being their orientation. Black holes point towards the future, while the Big Bang points towards the past. Black holes are like small universes embedded inside a larger universe. Black holes are like small universes embedded inside a larger universe. They are regions where the gravitational pull is so strong that not even light can escape, creating an event horizon, beyond which nothing can return. The universe we observe might similarly be embedded within an even larger structure, possibly a black hole in another universe. The cosmic string theory, while speculative, offers an intriguing alternative to the traditional Big Bang theory. It suggests that our universe could be part of an endless sequence of universes, each one born from the remnants of the previous one in an eternal cycle. This idea aligns with the concept of black holes, where matter collapses to an infinitely dense point, potentially creating a new universe inside. The similarities between the singularities of black holes and the singularity of the Big Bang are compelling. In both cases, we are dealing with points of infinite density where our current understanding of physics breaks down. Geodesic incompleteness helps illustrate this concept. In general relativity, a geodesic is the shortest path between 2 points in curved spacetime. Geodesics continue indefinitely unless they encounter a singularity, a point where the equations of general relativity no longer hold and infinite curvature occurs. At these singularities, all paths terminate. For the Big Bang, this singularity exists in the past, representing the beginning of our universe. For black holes, the singularity lies in the future, at the center, where all matter falling into the black hole is eventually crushed to an infinitely dense state. This duality suggests a profound connection between the beginning of our universe and the nature of black holes. Another intriguing aspect is the cosmic microwave background, CMB, radiation. The CMB is the afterglow of the Big Bang, the thermal radiation left over from the early universe, now observed as microwave radiation. It provides a snapshot of the universe when it was just 380,000 years old, offering critical evidence for the Big Bang theory. The CMB is uniform in all directions, indicating that the universe was once in a hot, dense state before expanding and cooling. The CMB and the event horizon of a black hole both serve as boundaries in our understanding of the universe. The CMB marks the limit beyond which we cannot observe, as light from further away has not had time to reach us since the Big Bang. Similarly, the event horizon of a black hole marks the point beyond which nothing can escape, not even light. These boundaries highlight the limits of our observational capabilities and our understanding of spacetime. They suggest that there might be more beyond these horizons that we cannot currently perceive. This idea aligns with the notion that our universe could be a part of a larger, more complex structure, possibly a black hole in another universe. To summarize, the cosmic string theory and the concept of black holes offer fascinating insights into the nature of our universe. They propose that our universe might be part of an endless cycle of creation and destruction, with each universe emerging from the remnants of the previous one. The similarities between the singularities of the Big Bang and black holes, along with the boundaries marked by the CMB and event horizons, suggest that our universe might be embedded within a larger structure, possibly a black hole in another universe. This perspective challenges our understanding of space, time, and the cosmos, opening up new possibilities for exploring the profound mysteries of the universe. What if the universe wasn't a large rubber ball but an enormous black hollow with a radius of tens of billions of light-years? We've struggled for many years to understand where this chaotic and outstanding mass of matter comes from. In this video, I want you to let go of familiar standards and theorems because the truth is that humanity is on the verge of finding solutions to the most complicated questions. The Big Bang theory might be incorrect, and we might be only a speck of matter inside a tremendously massive black hole. Join us on a bold journey as we explore a mind-boggling question. Could humans really exist inside a black hole? This is I-200M, a scientific channel delving into the profound mysteries of the universe. The concept that our entire current universe is a weird entity deep inside a black hole may sound a bit crazy, but it's not entirely unfounded. Going back to the time before the Big Bang, quantum physics suggests that all the matter we see today was compressed into an entity with infinite density, much like a strange point inside a black hole, which we can now examine. Scientists have a clear picture of the early universe called the Big Bang theory. In this model, a long time ago, the universe was much smaller, warmer, and denser than it is today. About 13.8 billion years ago, during the primordial period, everything that makes up who we are today was formed in the first few moments of the universe's existence, all from a tiny compact ball with limitless density, approximately the size of a peach and a temperature of over 1,000,000 trillion degrees. The idea of a universe arising from nothingness may sound highly implausible, but the evidence for it is quite convincing. Galaxies are moving away from each other like pieces of shrapnel from an exploded shell, and the lingering heat from the Big Bang remains present all around us, although it has cooled considerably due to the expansion of the universe. This afterglow doesn't appear as visible light. Instead, it exists as microwave radiation, the cosmic microwave background radiation, which was discovered by radio astronomers way back in 1965. Astronomers have done everything from observing the leftover electromagnetic radiation of the early universe to measuring the abundance of the lightest elements, and they have found that all these observations align with the predictions of the Big Bang theory. As far as we can tell, this is an accurate portrait of our early universe. However, the Big Bang picture is still incomplete. There is a missing puzzle piece. The earliest moments of the universe remain a vast mystery. The problem here is that the laws of physics we use to understand the early universe are a complicated mixture of general relativity and high-energy particle physics, but they can only take us up to a certain limit before a breakdown occurs. As quantum physicists try to delve deeper into the very early moments of the universe, mathematics becomes more and more convoluted. If we attempt to solve it, the complexity only grows until everything reaches a dead end. Consequently, the answer to the question, what was the universe like before the Big Bang, still lacks a reasonable solution. But now, I can present to you a rather appealing hypothetical solution. Let's embark on a journey back to the time before the formation of the weird point from the Big Bang and explore what really happened. We will also take a look at whether our current universe might be a world inside a black hole. Don't worry about doubting the accuracy of the Big Bang because we won't be focusing on it. Instead, we're going to delve deep into the cosmic string theory. The cosmic string theory is one of the significant theories concerning the origin and evolution of the universe. It proposes that before the Big Bang, our universe was not a unique point of origin but part of a never-ending sequence of universes existing within an endless chain. This theory was proposed by the American astronomer and physicist Alan Guth in the 1980s. He developed this idea to address certain questions that the Big Bang theory encountered, such as why the universe shows such perfect symmetry or why it has a spherical shape that means it is not contracting due to the gravitational pull of objects. According to the cosmic string theory, before the event of the Big Bang, there was no space, time, or universe as we currently know it. Instead, everything existed in an incredibly tiny and incredibly hot collapsed state, also referred to as a singularity. At the moment of the Big Bang, a very powerful event occurred called inflation, causing space and time to begin expanding suddenly and exponentially. The inflation period we know of lasted for a very short period, only around 10 to the power of negative 36 to 10 to the power of negative 32 seconds after the Big Bang. During this period, space expanded rapidly and abruptly, causing the universe to grow very quickly, leading to the uniformity and symmetry we observe today. It also explains why the universe has a spherical shape, considering the magnetic forces and negative gravity pulling the universe into a spherical shape during this phase. However, instead of stopping after some time like in the traditional Big Bang theory, the cosmic string theory suggests that the expansion never halted and continues infinitely. During this expansion, each new universe is constantly and cyclically spawned from the universe before it. Each new universe may have different characteristics and conditions, but they all still adhere to the general laws of physics. According to this theory, our universe is considered one of these universes in the endless chain. Although the cosmic string theory proposes a sequence of universes, each universe exists independently and does not directly influence or interact with others within our observable range. As a result, we cannot directly observe or interact with other universes in this chain. Alan Guth's theory shares many similarities with the concept of black holes that we are currently studying. In both cases, the Big Bang represents the strange point of the universe, and the process of creating baby universes mentioned in the cosmic string theory bears striking similarities to what humans think about black holes in space. While stars and galaxies operate under the influence of gravitational waves, we know that enigmatic phenomena like black holes may hide more dimensions of space, which is why entities beyond the event horizon can't observe the strange point inside it. It's similar to a black hole limiting our understanding of the strange point by making it impossible to escape. If an object falls into the region of the event horizon, nothing can prevent it from falling within the black hole. The same principle applies to our universe as well. Essentially, the universe expands indefinitely and always propels forward, causing everything to be unable to escape its radius. When observing it visually, we can't exactly determine whether the universe is expanding or galaxies are falling toward the strange point of this huge funnel. This scenario is quite similar to Galileo's story about whether the Earth revolves around the Sun or the Sun revolves around the Earth. To provide more accurate evidence on this matter, we have the concept of cosmic microwave background, CMB. It's a theory in astronomy related to observing and studying cosmic microwave radiation. The CMB is light emitted from the distant and early stages of the universe. It is generated from atoms formed within the early universe, allowing light to travel freely through space. Before that, the universe was a hot, dense plasma that emitted random light, but as atoms formed, the plasma became more transparent and no longer absorbed and emitted light randomly. The CMB is observed as microwave radiation with a very low temperature spectrum, about 2.7 Kelvin, which is about minus 270.45 degrees Celsius. This is the leftover light from the earliest time in the history of the universe after the Big Bang, and we can see it in all directions across the sky. The boundary of the CMB marks the limit of the universe beyond which light cannot escape. The similarity between the CMB and the event horizon lies in both being boundary lines in space and time. The CMB serves as the boundary for light in the universe, where light cannot escape the universe but can move freely through space. The event horizon is the boundary of a black hole where space is so curved that nothing can escape beyond it. Both are related to the expansion and structure of space and time in the universe. Thus, when considering it visually, the idea that our universe is a world generated inside a black hole is not entirely unreasonable or illogical. Rather, both CMB and the event horizon play crucial roles in the study of the origin and evolution of the universe. The CMB is one of the most important pieces of evidence for the Big Bang model, helping us understand more about the state of the universe shortly after its formation.